Hello students, welcome to our research classes, and today's topic will be on permutation groups, symmetry groups and alternating groups. But these topics are very hard because if answers are also provided in front of you, just by seeing that you may not be able to get the correct one. So this one is a little bit of challenging one. So that's why we will start right away with respect to the types one after another. So what is this permutation group? Okay, so if a problem is solved, then also you are not understanding, so you need to know that there are some basic points which is missing. So I will start with the basics. So what is a permutation group? Is that to do with the permutation and combination? Well, yes, a group whose elements are permutations is called a permutation group. That's it. A group is a set so whose elements can be permuted. Now what is this permutation? I will coming to this. For example, the set Pn of n different permutation, n different ways you can form the structure, and remember that 1 2 and 2 1 are two different permutation, and all forms on elements form a group with respect to the permutation multiplication. Okay, remember that the identical permutation or the structural permutation, the identical permutation I can be written as a1 a2 dot 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 an, and here also a1 a2 dot 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 an. So if it uses two rows and they have the same elements exactly in the same ordering, then this is called an identity in Pn elements. Okay, now if in the permutation group, I'm giving you some basic idea, ak and bk, so this is a matrix form, and a inverse is obviously then bk ak. So in this case, if you do that, a into a inverse, you get ak and ak, and we have seen that if the same thing, this becomes an identity. Okay, so since a inverse, this a inverse belongs to Pn, so the inverse of each Pn actually exists. So this is the basic pattern based structure, and product of two permutations of the same n objects is a permutation of the same objects itself. Okay, so if it is p equal to a b c dot 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 in this group, so the set of different permutations of n objects are like a1 a2 dot 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 an. These are the permutation structures. Order of p, obviously n factorial. So this is nothing but the number of elements in this permutational group. This thing, when it is non-commutative, this is MCQ special, non-commutative. If n is greater than or equal to 3. This thing is applicable because 1 factorial is 1, 2 factorial is 2. So from 3, this thing is not equal to 3. So that's why it has to be n greater than equal to 3 in order to get a permutational structure. You may think in that way. There may be a long proof. I just give you the shorter idea of this. Now what is a symmetric group? So if in the set Pn, maybe all permutations, so in case of symmetricity, so if all permutations of degree n is a finite non-abelian group, I have done in the previous video, group of order n factorial with respect to multiplication, then it is called a symmetric basic structure. So what is alternating? So in case of alternating, the set an of all even permutations of degree n is a finite non-abelian group. It is known as the alternating group of the order n factorial by 2. It's only even, that's why it's half of the order, and it's a subgroup of the symmetric group. So this is a subgroup. So an alternating group is a subgroup of symmetric, and both are non-abelian. So if the permutations of 1 2 3, so what are the possible permutations of 1 2 3? Okay, maybe P0 I write 1 2 3, I write 1 2 3. So this is one way of writing. P1 I can write it as 1 2 3 1 3 2, change this position. maybe P2 is another 1 2 3 2 1 3, and P3 maybe 1 2 3 2 3 1. So what I'm doing here, so I'm not changing the above part, and I'm just changing the position of 1 2 3. We know there are 3, so obviously factorial 6, factorial 3, that is 6 possible ways to write it. So with respect to the first position, how can you change the group's position and can get some different combination? That's it, that's what I'm making here. So P5, as I started with 0, so 1 2 3 3 2 1, this is it. So P3 means 3 elements are there, as P0, P1 dot dot dot, P6, P5 is a symmetric group, right? All this is a symmetric structure, and A3, P0, P3 and P4 is an alternating group. Now what is this called? This alternating thing is coming. So you P0, you see this P0, this is P3 and this is P4. So what is the alternation coming? This is alternation because of one reason. For example, you take a circular structure 1, 2 and 3. Isn't this a pattern 1, 2, 3? And I said that if you change the position, it will change. So starts with 1, then 2, 3. If it starts with 2, then 3, 1. Starts with 2, 3, 1. If it starts with 3, then 3, 1, 2. That's it. But this thing is not. Because if it starts with 3, then in this ordering, it's not going. If it starts with 2, then this ordering is not going. That's it. So alternating group is, so wherever you start, but it follows the main circular pattern. If it is 1, 2, 3, 4, starts with 4, then 1, then 2, then 3. Then if it starts with 2, then 2, 3, 4, 1. That's it. So now you are okay about alternating group and symmetric structure. But what happens if it is 4, 1, 2, 3, 4 and I said like 4, then 2, then 3. Remember that in that case it's not symmetric. If you leave out one thing, and I already said that an alternating group is a subset to the symmetric. So if it is not symmetric, you can't get an alternation as well. Okay, so now going to the next part here. So some interesting groups are obtained by symmetrical movements of geometrical figures. Okay, and these are group of symmetries. Okay, so let me draw that in one of those interesting figures. Okay, which you possibly will recognize easily. Remember that my approach is as easy as possible with respect to the idea of simple grassroots level mathematics which you have. Okay, so ABC, this thing, this may be A, C and B, this may be here A and C and B, this is A, B and C, this is A, B, C, this is A, this is B, this is C, and this is A, B, C. So many different organizational structure is happening over here. So in this kind of diagrams, obviously how many are there? 6. So there are 6 possible ways of forming. I have done it already with the P1, P2, P3, P4 and P5. So for example, they may ask you find the group of symmetries of all equilateral triangle for the rotation through 0 degree, 120 degree and 240 degree in the plane about the line through the center of the reflection of the rotational space or flip or anything. So all you have to do is change the pattern, change the structure, and it follows this. Okay, you can write it. So we will come again to this kind of diagrams. Let me give a relatively easier portion first. Remember that the identity based structure doesn't always a rotational based structure. For example, the first rotation is like this. The second rotation may be like this. This is only 90. This is 180. Third time the rotation is giving you 270. And the fourth time the rotation is giving you 360. Even this rotational structure is over time is giving you this. So the rotation is always with the same starting point and ending points are only different, but their movement pattern is always the same. Okay, so here is the basic formational idea.